In this video we are going to discuss a theorem that is an application of derivatives, and that is called Rolle's theorem. And so in order for Rolle's theorem to apply to a function, three conditions have to be met. If all three of those conditions are met, then the conclusion will be true. So first of all, your function f has to be continuous on a closed interval. It has to be differentiable, which means you can take the derivative at every point on that function over that open interval. So differentiable at every single point except for the endpoints of that interval. That's why it's an open interval there. And then the third condition is that f of a has to equal f of b. So what that means is the y value at the endpoints of your intervals have to be the same, right? So those two y values need to be exactly the same, is what condition 3 says. If all three of those conditions are met, then it says there is a number c in the open interval from a to b. So there's some x value in between a and b such that f prime of c is equal to 0. So here are some examples of Rolle's theorem and what that's going to look like. So we have four different looking functions here that are graphed, and they're all graphed over an interval from a to b. And in each case, f of a is equal to f of b. Notice in all four of these graphs, the y value at a and the y value at b are the same. Okay, now obviously they could be doing different things in between, but the y values at those endpoints are exactly the same. So because these are all continuous, they're all polynomials, so they are all differentiable over those intervals, and f of a is equal to f of b. It met all three of these conditions. In every case, there is a number c in between a and b where f prime of c equals 0. Now, this f prime of c equals 0 means we're looking for those places where we have peaks or valleys, where we have those local extrema, and that's what we're seeing here. Okay, so if you think about it, if I go from a y value and my function is continuous and also differentiable, which means there are no cusps, right? So no sharp points. But if I have to end up then at the same exact y value, then at some point I had to hit a local maximum or a local minimum. And it is possible that there's more than one c value, as you see in this third example. That happens twice. But I'm hitting those local max or local minimums, which means I have horizontal tangents at some location in between a and b. Now this first example is just a horizontal line, but then I could have a c value really anywhere in between a and b, where I would have a horizontal tangent there. So that's the idea of Rolle's theorem. So what we're going to look at is we are going to look at functions. We're going to verify that it meets the criteria, and then we're going to find those c values that should be somewhere in between our interval that would give us those horizontal tangents. So here's our function, f of x equals x cubed minus x squared minus 6x plus 2. And what we are going to do is we are going to first verify the conditions. So the first condition, I have to say that f is continuous on the closed interval from 0 to 3. Now, you may ask, well, are we sure that it is? And my answer to that is it's a polynomial, and hopefully at this point in time in this course you understand that polynomials are continuous everywhere. Therefore, it is continuous on the closed interval from 0 to 3. So I'm just going to say f is continuous on 0 to 3. 2. The same thing for differentiability. So f is differentiable differentiable on the open interval from 0 to 3. And I know that because, again, it's a polynomial, and that means we're not going to have really any, if it's continuous, we're not going to have any jumps, any breaks, any sharp points. So I know that I'm going to be able to take the derivative at every single point along that function over that interval from 0 to 3. The third thing that I have to say is I have to figure out the y values at the endpoints of my interval. So what is f of 0? Well, if I plugged in 0 into my function, that's pretty easy. I get 2. I just get the constant term. And if I plug in 3, we're going to get 3 cubed minus 3 squared minus 6 times 3 plus 2. So that's 27 minus 9 minus 18 plus 2. If I add all that together, I get 2. So f of 0 and f of 3 are the same, so it does meet the third condition as well. The y values at the endpoints are the same. So it met all the criteria, so then I can apply Rolle's theorem. That tells me then that there is a number c in. So I'm going to say that part first, and then we'll find out that. And then we'll find what those values of c are. So there exists a number c in the open interval from 0 to 3. So c is not going to be at the endpoint. There exists a number c in the open interval from 0 to 3 such that f prime of c is equal to 0. Okay, so then it asks us to go ahead and find all the numbers c that satisfy that. So what I need to do then is I want to find what are the c values where f prime of c is equal to 0. Okay, well, that means I need to find f prime and then also set it to 0. So f prime, and I'm going to do f prime of c because that's what we're looking for, is that c value. That would be 3c squared minus 2c minus 6, and I want to set that equal to 0. I'm going to use the quadratic formula to find this. So c is going to equal 2 plus or minus the square root of 4 minus 4 times 3 times negative 6 all over 2 times a, which would be 6. So that's going to give us that c is equal to 2 plus or minus the square root of, if I multiply out that inside and combine those, I'm going to get 76 over 6. So c is going to equal 2 plus or minus 2 square roots of 19 over 6. 2 plus or minus, let me go ahead and simplify that. That's going to be 1 plus or minus the square root of 19 over 3. Okay, now we're saying that this is the value of c. We want to make sure that the c value, we're looking over the interval from 0 to 3. And I have plus or minus here. So I'm saying there are two c values. Are we positive that both of those are in the interval from 0 to 3? And to help us with that, I've used Desmos just to show you what's going on. So I have graphed the function. It's x cubed minus x squared minus 6x plus 2. And what I'm going to do is I'm going to only graph this over the interval from 0 to 3. Okay, so if I only graph that over the interval from 0 to 3, this is what I see. Now, we had 1 plus the square root of 19 over 3, which we see happens down here. And then we also have 1 minus the square root of 19. Now, if I delete this, you can actually see it better here. This second point happens here at the top. So only one of those happened over the interval from 0 to 3, and that is the positive square root. So I go back here, and c is not going to be both of those because we're talking specifically over the interval from 0 to 3. Our c value is simply just going to be 1 plus the square root of 19 over 3. Okay, so again, steps there. Make sure that you verify that it's continuous, differentiable. Make sure the f of a equals f of b. And then you're going to find the derivative, set that to 0, and solve for those c values, verifying that those c values do occur in the interval that was given.